Have you ever seen the comedian Jim Gaffigan talking about Hot Pockets? It's pretty funny, but I need to go back and rewatch it before I show it to you as a class. So, because he's generally pretty clean, but I don't want to get myself in trouble for anything. So anyway, if you are familiar with the Hot Pocket, his main premise is that you can only have, in his little comedy skit, is that you can only have Hot Pockets two ways, either still frozen in the middle or molten lava hot. It's hard to get them right. So a Hot Pocket is removed from the microwave and set on the table to cool. The rate of change of the Hot Pocket's temperature with respect to time is proportional to the difference between the Hot Pocket's temperature in degrees Fahrenheit and the room temperature of 73 degrees. And if we get time after the AP exam, we're going to do a lab with this. We'll use pizza rolls or Hot Pockets or something of the sort to test cooling time, and we will eat them, yes. Because if you ever, like when you microwave things, it'll give you a cooling time. It'll say wait 2 minutes. But as Daniel Bautista last year proclaimed that, what was he always wanted to say? He had some saying. He said that if you're a real man, you're just going to eat it right out of the microwave. There, he burned his mouth pretty bad during our lab, I think, because he was going to do that. But he would not admit it. But anyway, so they will all say like how long to let it cool, but Newton's law of cooling, of course, could help us have the precise amount of time to have your pizza roll or your Hot Pocket at the optimal temperature, which could be very important. So it says write a differential equation that describes this relationship where K is a constant. So this is Newton's law of cooling, but it didn't give you Newton's law of cooling. It gave it to you in this wording. So if you kind of read through the rate of change of the Hot Pocket's temperature, capital T, with respect to time, lowercase t. So that rate of change of capital T with respect to lowercase t is just dt over dt. Is proportional to, so that equals K, the difference between the Hot Pocket's temperature in degrees and the room temperature of 73 degrees. So the Hot Pocket's temperature is capital T. The room temperature is constant at 73. So this is Newton's law of cooling. It says the rate of change of temperature is proportional to the difference between the temperature of that object and the ambient temperature. So you could see a problem like this where it doesn't tell you it's Newton's law of cooling, but it is in fact Newton's law of cooling. So more information here. 20 seconds after being removed from the microwave, the temperature of the Hot Pocket is 205 degrees Fahrenheit. 1 minute after being removed from the microwave, the temperature of the Hot Pocket has dropped to 187 degrees Fahrenheit. Estimate how long it would take for the Hot Pocket to reach the optimal eating temperature of 150 degrees. Okay, so for this, the first thing we're going to need to do is solve this differential equation. So we've got dt lowercase dt equals K times t minus 73. So we would need to multiply both sides by that lowercase dt. We got to get the capital T over to the other side. We will do that by dividing. So we've got dt over t minus 73 equals K dt. Okay, everybody all right here? We will integrate both sides. Over here on the left, we will get natural log of the absolute value of t minus 73. And over here, we're going to get K lowercase t plus c. And it will probably be in our best interest to go ahead and solve this for that capital T. So if we do e to the power on both sides to get rid of that natural log, we'll have capital T minus 73 equals this c can come out front as our coefficient, and we'll have CE to the KT, and then we'll add our 73. There. Okay, so once we get this, we need to start plugging in information. We got 20 seconds after being removed from the microwave, the temperature of the hot pocket is 205. 1 minute after being removed, we got 187. So there's some reasons why I've done this the way I did, and we're going to have to adjust some things because of it. So if you take a hot pocket out of the microwave, I've learned this from our actual experiment that we have done. If you take a hot pocket out of the microwave, then it's going to take the thermometer a minute to register. So you can't find the temperature right after you take it out of the microwave unless you've got some high-tech devices that are microwavable and will give you the temperature instantly. So by the time you actually get the temperature, it's probably like 20 seconds after you've taken it out. Now here's the problem. Our equation is T equals CE to the KT plus 73. I'm going to do this real quick, but don't plug it in. If I plug this information in, 205 equals CE to the K times 20 plus 73. I'm not going to be able to solve that because I will have a C and a K. So I will not be able to solve it for a variable. So I'm going to have to make some adjustments to this so that I will be able to solve it. Any ideas on what we could do? Okay. The only way we're going to be able to solve this is if there's only one variable. And in the other problems we've done, there's only been one variable to solve for in that first step because time was 0, right? We let like that initial temperature read and our time was 0. If time was 0 here, if that was 0, then I'd have K times 0 and the K would go away. And I could solve for my C and then worry about my K. So what we're going to have to do is we're going to have to let 205, that initial temperature, we're going to have to let that be time equals 0. Right, so rather than doing what I've done here, now you can write down what I'm doing. We're going to have 205 equals CE to the K times 0 plus 73. So we are letting that 20 seconds actually be 0. What does this mean about our answer that we're going to get at the end? We're going to have to add, it's going to be 20 seconds off, right? So we're going to have to add another 20 seconds to it whenever we figure out what time we need this to rest. So we're going to keep in mind that 20 seconds has actually been called T equals 0. So we might want to make ourselves a note. 20 seconds is going to be T equals 0. It's the only way you're going to be able to solve this because otherwise you got a C and a K. Well, I mean, there might be a possibility. I guess you could do like a system of equations sort of thing here, but particularly without like graphing it on Desmos, that's not going to be easy at all to do. So, so we're going to do this instead. It'll get us around having to deal with that. So this is just going to be 1. We got 205 is going to equal C plus 73. We are going to subtract our 73. And we will get 132 is our C. So we got T equals 132 e to the KT plus 73. So we have found one of our unknown variables to be 132. We now need to find the k so that we have an equation that we can use. So this is where we're going to use our other piece of information. 1 minute after being removed from the microwave, the temperature of the Hot Pocket has dropped to 187. So I'm going to plug in 187 for my capital T. What do I plug in for T? 40. Because 60 seconds, because we let T equal 0 be 20 seconds, it is going to be 40 there. Okay, so only one variable in this equation. We can solve it here. So that will give us 115 equals 132. E to the 40k. We'll divide by 132 to get the calculator out here. Oh, it is 14. Thank you. Let's fix that. Put our calculator over here. And 114 divided by 132. It's going to give us 0.863. Keep that in your calculator. E to the 40k. How do we get rid of the e? Natural log. Oh wait, that doesn't cancel. So if we do natural log of that answer that we just got, we're going to get negative 0.1466 equals 40k. And then we just have to divide by 40. And we're going to get k equals negative 0.003665. It will be in your best interest to store that as a k, or whatever letter you want to use, but I would suggest k, since you're calling it k here. So that way you don't have to type in that number. So now we have our equation. Our equation is T equals 132e to the negative 0.003665 t plus 73. All right, everybody good here? All right, our last step is to figure out when we will reach that optimal temperature, which has been declared to be 150 degrees. I'm going to put a K there as I work this out. So you subtract that 73, that is going to give you 77 equals 132 e to the kt divided by 132. 77 divided by 132 is going to give us 0.583. Repeating is e to the kt. We will do natural log of both sides. That will give us negative 0.5389997 equals kt. Remember, k is actually a number now that I have stored in my calculator. So I'm going to divide by that k, and I will get 147.062. For my t, this is in seconds. But remember that I let 20 seconds be 0. So what should I do with this answer here? Add 20 seconds. So 167.062 seconds is how long you should wait, or if you divide it by 60, we could say 2.7. No, because you subtracted 20 from it in the beginning. So like the answer that we have here, this is how long you need to wait from t equals 0, right? Which t equals 0 is actually 20 seconds. So if we want the time since it came out of the microwave, then we would need to add that 20 seconds back, right? So 2.784 minutes if you want. So if you want the precise, perfect hot pocket temperature. Pretty much for Newton's law of cooling, you are always going to have to give it a like initial value where your time is 0 for that. So if it doesn't give you that, then you would need to make one of your values. Okay, questions? All right, so let's look at our notes for today. All right, so we are going to see a lot of exponential application here, and what we're going to see for a lot of these problems, I think probably all of them, if I'm remembering correctly, is the model for exponential growth and decay. And I have seen some of these show up. Usually it's in multiple choice questions for the exam. I don't think I've seen one on the FRQ part that I remember. So the model for exponential growth and decay arises from the statement, the rate of change of a quantity is proportional to the size of the quantity. So if we let quantity be our variable here, let's use a Q. The rate of change of a quantity, which we could call dQ dt, is proportional to the size of the quantity. All right, so it's the rate equals K times whatever variable is in the top of that rate, whatever value. Okay, so what you may see here is that it may say something like this: the rate at which the population of a town grows is proportional to the size of the population. And then it's going to give you data points. In 2000, the population was 6,000. In 2010, the population had grown to 6,522. So, the rate at which a population of a town grows, that is dP dt if we use the word, or the capital P for population. So dP dt is proportional to, so equals K times the size of the population, which is just capital P itself. So, the first thing that it asks us to do is to find the rate of change of the population. And so We don't want to just find like the slope between the 2 points that they give us there. That would be a rate of change, but it would be our average rate of change. It is looking for the rate of change exponentially that is happening here. So if they were wanting average rate of change, they would say average, and then you would just use 2,000, 6,000, and 2010, 6,552, and find that rate of change there. So what they're looking for here when they're talking about that rate of change is really this K value right here. So what you're going to have to do is solve this differential equation. So to do that, we would multiply both sides by dt. Cancel that dt out. And then we got to get this capital P over here to the other side, so we'll divide by capital P. So that leaves us with 1 over P dP equals K dt. We will integrate both sides, and we will get natural log absolute value of P equals K T plus C. And we will do e to the power on both sides, and we will get the capital P equals CE to the KT. The capital P was over here on the right-hand side. So to get rid of it on that right-hand side, because we need it to be over here with our P, we're going to divide both sides by that capital P. So you could write it as dP over P, or you could just put a 1 in the top. Either one is fine. Now, what you're going to see on these problems is that it's going to be exponential growth every time. If you're having a rate equal to or a rate proportional to the variable that you're talking about for the rate. So the rate of change of the population is proportional to the population, or it could be the rate of change of the weight is proportional to the weight. It's just exponential growth or decay is what you're looking at. So it is okay, unless they specifically ask you for a differential equation, it is okay to skip to CE to the KT, because that's what you're going to get every time for this. If you have a rate equal to K times that same variable, you're going to get CE to the KT every time. So while we did that on this problem, if it's worded that same way, it's okay to skip down to P equals CE to the KT. Now this becomes something that you guys could have solved in pre-calculus, because we use that PE to the RT, and we found some of these questions. So if we're looking for that rate of change, the first thing we're going to have to find is the C. What is the C always end up being for the exponential problems? It is a constant. Particularly in context, it's going to be your initial value, what you start with. And whenever we did, a lot of times it was PE to the RT. P was our principal value. So you can plug in. We're going to let 2,000 be T equals 0, and 6,000 would be the P at that time. We're going to let this be T equals 10. You can use 2,000 and 210, but it just makes it much harder. So if we let that be T equals 0, it's our initial value. We're just going to get 6,000 for that initial C. You can do the work to plug that in if you want. The C is going to be your initial value every time for just straight exponential problems. So now we need to find the K, because that is the rate of change of our population. So we're going to take our other piece of information, which is T equals 10, and the population is 6,522, and we're going to plug that in. So 6,522 equals 6,000 e to the K times 10. All right, we just have an exponential to solve here, so we're going to divide by 6,000. Okay? Natural log of both sides. All right, back with us. We're going to divide by 10. And K is going to be 0.008342. The question when it asks for a rate of change, though, is looking for a percentage. That is not a percentage. It's your decimal. What percentage is that? 0.8342% per year. Questions there? That constant proportionality is going to be your rate of change in these types of problems here. So whatever, if you think about like the ones that we did back in pre-calculus, the formula we used was called P(e) to the RT. So just because of the variables we use with differential equations, that C is actually the P right here, your principal value, and that K ends up being the R, the rate for that. Okay, so if you need to make a prediction, let's store this value as K so that we don't have to type it in again. All right, so we've stored that value as K. If we need to predict for 2025, all we have to do is do 6,000 e to the K is a number. I'm going to put that in the calculator, and for 2025, I would just put in 25. So you would just type that into the calculator, 6,000 times, e to the K times 25, and we'll get 7,391.37, and they would probably want you to round that to the population. So 7,391. Okay, questions? All right, so this is a naked problem, no context. The rate of change of y is proportional to y. So dy dt equals k times y. So rate of change of y is dy dt. Is proportional, tells us to put equals k. And it's proportional to the variable y. So if you see it set up like this, you can see you've got a dy dt, just k times a y over here. You can solve the differential equation if you want. These are usually multiple choice questions, so the work is not going to matter. Now, if it tells you to write a differential equation for this and then ask you to solve, you will have to write that differential equation. Otherwise, this is basically the same differential equation we just solved, except for using y's instead of p's. You're going to get y equals ce to the kt. Okay, so you're looking at exponential growth or decay here. And so it gives you information that you can use. T equals 0, y equals 2. That right there is your initial value, which is your C for these problems. So we can do y equals 2e to the kt. It tells us next that when t equals 2, y equals 4, we're going to plug this stuff in to find our k. So we'll have 4e equals 2e to the k times 2. We'll divide both sides by 2. 2 equals e to the 2k. We'll take the natural log of both sides. Just in case they do this, I'm going to natural log of 2 equals 2k. We'll divide by 2. So natural log of 2 over 2 is our k. You can put in your calculator and get a decimal. I'm going to work it out and just see how it works out without doing this, in case maybe I think it's still going to require a calculator. But we'll see. So our equation that we're getting here is y equals 2e to the natural log of 2 over 2 times t. And so it wants us to tell when we will get a value, or what the value will be whenever we have t equals 3. So we're just plugging in 3 there. Y equals 2e to the natural log of 2 over 2 times 3. And if we type that into the calculator, 2e to the natural log of 2 over 2 times 3. So that's right. Yep. We get 4 square root of 2. Anybody know how we could do that without a calculator? How we could get that answer without a calculator? We're at like this, 3/2 natural log of 2. E's and natural logs cancel each other out, right? But not with that 3/2 as a buffer. So what can I do with that 3/2? It can. So I can move this inside as a power, which would be 2e to the natural log of 2 to the 3/2 power. Now the e and the natural log do cancel. We get 2 times 2 to the 3/2, which if I write that as a square root, it's 2 times the square root of 2 to the 3rd power, which is 2 times the square root of 8. 8 breaks down into 2 root 2, and we get 4 root 2. Say that again. Right here in your exponent, right here where you got that 3 in the numerator, it's like a 3 over 1. So, what? This is just what I got with the calculator. So, this is an alternate method if you were to see this without a calculator. So, if you got the calculator, type it in. Don't try to do that by hand. So if you have the calculator, just type it in. But sometimes they give you the stuff calculator inactive. So I wanted to look at it both ways. Okay, questions? So you can, with exponentials, whatever your initial value is always going to end up being that c. So like when I plug this in, what's going to happen is I'm going to have y equals c e to the k times 0. And oops, I should have plugged in a 2 over here. And so what's going to happen every time on these exponentials is that e to the k times 0 is 1, and you just get that initial value. So it doesn't happen with things like Newton's law of cooling, where you've got like it's not k times just that variable. You got that plus 73 or whatever on the end. So you have to actually figure it out for those. But if it's a straight exponential problem like this one right here, you can just take whatever that initial value is and plug it in for your C without showing any work for it. But if you do work, of course, it doesn't hurt anything. Okay, questions? All right. So the rate at which a radioactive substance decays is directly proportional to the amount of the substance. 10 grams of the plutonium isotope 239 were released in a nuclear accident. The half-life of this plutonium is 24,100 years. How long will it take for the 10 grams to decay to 1 gram? Okay, so this is exponential decay. They're not going to like on the problems you're going to see, they're not going to just tell you this is decaying exponentially. If they did, then you could go straight to that. That's like these problems are no different than the problems you did in pre-calc, except for the way they introduce it at the beginning. But when they say the rate that it decays, so the d, what variable do we want to use for this? Dx dt, really could use any variable, but we'll use x, is proportional to that value, that amount of the substance, which is our x. So if you solve this, you will get x equals CE to the KT. Right? You can actually break it apart and solve it if you would like, but this, whenever you see the rate and the variable over here matching, and the only thing you have is the K, it's just going to be exponential. So the initial amount that is released is 10 grams, so we just plug that in. So x equals 10e to the KT. And we want to know how long it will take for their, we know the half-life is 24,100 years. How are we going to use that? What does the half-life tell us? How long for half to be gone? How much is half in this case? 5. So we're going to plug in 5 for our x, and our t is this 24,100. And so we will divide by 10. We will get 1/2 equals e to the 24,100 k. We'll do natural log of both sides. We'll get negative 0.69314 equals 24,100 k, and we'll divide by 24,100. And storing this is going to be really important on a problem like this because our decimal is so tiny. We got 0.000029 is our k. So if you round that off, because we're dealing with like such like long periods of time, it's going to throw it off quite a bit. So you want to store this value as your k. And so now we want to know how long it will take for there to be only 1 gram. So our equation now is x equals 10e to the kt, but k is actually a number now, right? K is that number. And so we will say 1 equals 10e to the kt. We'll divide by 10. 0.1 is going to be e to the kt. We'll take the natural log of both sides. We'll get negative 2.30259 equals kt. t, we will divide by k, which is actually negative 0.00029. So if we divide that by the k, we will get 80,000. 58.5 years. And I think I actually looked that up, so that's actually accurate. It seems like I looked that up. If I want to verify. And that is why nuclear energy is scary to people. Okay, questions? All right, last one. Experimental population of fruit flies increases according to the law of exponential growth. So if you see something like this, the law of exponential growth is going to indicate that you are using y equals ce to the kt. So this is an example where they did not give it to you as the rate being proportional here. They just said exponential growth. I don't know if you're going to see this like on the exam or not, but it's possible. There were 100 flies after the second day of the experiment and 300 flies after the fourth day. Approximately how many flies were in the original population? Okay, so this one's a little different. What do you guys think we should do? We're going to have to work backwards. And we really need to, we've got to be able to find a C, right, for our equation. So we're going to have to do a lot like we did with our Hot Pocket problem. And we're going to have to let 2 days be t equals 0. So we're treating it like our 2-day amount is our initial amount. So that means we'll have y equals 100 e to the kt. But we're keeping in mind that what we're calling the initial amount for our equation is not actually our initial amount. So the actual initial amount, what is it going to be? What's t going to equal then? -2. All right. So we're having to adjust that so that we can find the correct value here. So after the fourth day, we have 300 flies. So 4 days, we're going to treat that like t equals 2. You may even need to write this down to keep it straight because it's easy to get mixed up on this. So we'll have 300 equals 100 e to the kt. We've got to divide by 100. 3 equals e to the kt. We will do natural log of both sides. Natural log of 3 equals, I should have plugged in 2. And we will have 2k. Divide both sides by 2. So natural log of 3 over 2 is our k. So our equation is y equals 100 e to the natural log of 3 over 2 times t. And for our initial population, we actually need to plug in -2 for our t. So for the fun of it, let's try it without a calculator. We got e to the natural log of 3 over 2 times -2. If I multiply the stuff together in the exponent there, it is going to give me -2 natural log of 3 over 2, and those 2's could cancel. So it's going to give me 100 e to the negative natural log of 3. I can almost cancel my e and my natural log, but I can't exactly because of that negative right there. So what could I do with that negative? That negative is actually a negative 1. I can take it and pull it in as an exponent. So that will give me 100 e to the natural log of 3 to the negative 1. Which now the e and natural log will cancel. So I got 100 times 3 to the negative 1, which is 100 times 1/3, so 33.3 repeating, so about 33 flies. Now this particular problem, we might could have figured out without doing that work, because from 100 to 300 for 2 days, the population tripled, right? So if we went backwards 2 days, we could divide by 3. That would not be the case if you didn't have equal time increments. You would have to use the equation for that. All right, questions? All right, your assignment comes from the textbook, and let me make sure that I've got everything right on that because I didn't go check this assignment. 283. Got 1938. 51, 52, 56, 63, 64. Yeah, those should be fine for that. Keep in mind anything that is just straight exponential, you can go straight to y equals ce to the kt. You do not have to solve the differential equation for that. These last two, 63 and 64, those are going to be Newton's law of cooling. So they actually come from the section before. And this is our last section